Okay, so we're going to take a look at section 2.3, the sine law. And just to review, when you have a right triangle, okay, that means a triangle that has 90 degrees in it, you can use SOHCAHTOA to solve for any missing sides and angles, right? So you know that sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, and tan of theta is opposite over adjacent. Now, you can only use these ratios when you're dealing with a right triangle. Well, what happens if you don't have a right triangle? Because SOHCAHTOA doesn't work on triangles that are not right triangles. Well, that's where the sine law comes in, and then on for section 2.4, the cosine law. So you would use the sine law and the cosine law to work with triangles that are not right triangles. Okay, so the sine law then. The sides of a triangle are proportional to the sides of the opposite angles. This is what it looks like. The sine of angle A over the side A is equal to sine of angle B over side B, which is equal to sine of angle C over side C. Or you can write it as A is to B is to C, as sine of A is to sine of B is to sine of C. So the sine law is used to find unknown sides and angles if you have one of the following two situations. So you can have two angles and one opposing side, and two sides and one opposing angle. And we'll take a look at that a little more closely on the next page. So don't lose that thought there. Okay, so let's derive the sine law. So let's say you have a triangle ABC, so here it is, and you draw an altitude AD perpendicular to BC. And this symbol, this upside down T, means perpendicular to, which means it meets at 90 degrees. So AD then is the altitude of the triangle, which just means it's the height, so we can call AD H. So what we formed are two triangles. We formed AB and D and AC and D. So in triangle ABC, let's find sine of B. So sine of B then is H over C. And if I isolate for H, okay, meaning that I should multiply both sides by C, so I can reduce the C's over here on the right, then I get that H is equal to C times sine B. And in triangle ACD, let's find sine of C, which is H over B. And if I want to isolate for H, then I would multiply both sides by B, so I can reduce the B's on the right. And that means that H is equal to B times sine C. So what I've done is I've come up with an expression for the height for both triangles ABD and ACD. Now notice that both read H equals. So what we want to do is relate these two equations because both are equal to H. So that means I can take sine of BC and make it equal to B of sine C. And as you can see, I can rewrite this. So let's start by dividing both sides by sine of B. Okay, then I can reduce on the left. And let's say that I divide the right by sine of C and the left by sine of C, then I can reduce my sine C's, and as you can see, you are left with C over sine C equals B over sine B, which is here. And this is part of the sine law. Okay, so if you go back up here, okay, it's actually this part of the sine law. Okay, it's just that it's flipped, but they still are equivalent to each other. Okay, and if you draw the altitude from C and using similar steps, So what that means is if you take your triangle from here and you draw an altitude from C to AB and go through the same steps that you did up here where you had triangle ABD and ACD, then you can come up with A over sine of A equals B over sine of B. So therefore, we can just equate everything, right? A over sine A equals B over sine B equals C over sine C, or you can put sine A over A, sine B over B, and sine C over C. Okay, so now we're going to take a look at when you would use the sine law. There are two situations where you would want to use it. One is when you are given two angles and one opposing side. Oops. And the second situation is when you are given two sides and one opposing angle. Okay, and I'm going to use congruency conditions to show that. Okay, and what we mean by congruency conditions is that our triangles are uniquely defined. Okay, so it means that the triangles are uniquely defined. Okay, so that means that if I have this information that's given to me, then if I were to draw another triangle with exactly the same information, they would both have the same angles and the same sides and therefore have the same shape and the same size. Okay, so the first situation is where I would have an angle, angle, side. So A stands for angle, S for side. So the information that's given to me is given to me in this order: angle, angle, side, or side, angle, angle. Okay, whether I read it forwards or backwards doesn't matter. Okay, so I would go from an angle measurement that I'm given to an angle measurement that I'm given to a side that I'm given. So angle, angle, side, or if I like side, angle, angle. Okay, so if I were to draw a second triangle with exactly that same information, these two triangles would have the same shape and the same size. Okay, now in terms of the sine law, it's really important that you have a given side opposite a given angle. Okay, so if you have that situation, then you could use the sine law. Now if you take a look at the second diagram here, we have an angle, side, angle. So we have a given angle, a given side, and a given angle. And remember, it doesn't really matter which order I read it in, so angle, side, angle. But on this one here, I have a side of 6, but I don't have an opposing angle. But because I already know two angles in this triangle, I can easily work this one out, right? So I could just go 180 minus 80 minus 30, because I know all angles in a triangle add up to 180. And when I go 180 minus 80 minus 30, I would get 70 degrees, so I would know that this triangle, or sorry, this angle here is 70 degrees. And so now I have a side opposite an angle, or an angle opposite a side. Now, if I were to draw a second triangle with exactly the same information, I would get exactly the same triangle. They would both be the same size and the same shape. Okay, and just this chart, for some reason my 2 is lost here, so you can put 2 here for two angles that are given. Okay, now our second situation, we are given two sides and one opposing angle. So what's important here is that your angle that you're given is not contained. In other words, the angle that you are given is not between the two sides that you already know. Okay, so how you would read this, you would go side, side, angle. If you want, you can go the other way around, angle, side, side. But what's important here is that a side-side angle is not a unique situation. Okay, it can be, but at the same time it might not be. Okay, so in this situation you may or may not have a unique triangle. Okay, so what does that mean? That means that you can still use the sine law because you have an angle opposite a given side, so you can still use it, but you may not get a unique triangle. You may have to check to see if there is another triangle that's possible in the same situation. Okay, so they won't be unique. So we call this the ambiguous case. Okay, so in the next couple of videos we'll take a look at how we can use the sine law. Okay, so let's take a look at a couple of examples where we can use the sine law. In the first example, we're going to look for a missing side, and in our second example, we're going to look for a missing angle. And in order to solve any triangle using, or solving parts of any triangle using the sine law, you want to use proportional reasoning, which is to cross multiply. Okay, so we first need to decide if we can use the sine law or not. You're not always going to get all your triangles grouped so that all the ones that you can use the sine law on are grouped together, and all the ones that you can use the cosine law are grouped together. So they're going to be mixed up, so you need to decide whether you can or cannot use one of the two laws. Okay, so if we go with our table above, we can see that this is a side. Here's our side, and then angle, angle. Okay. Or if you like, you could read angle, angle, side. Either way that you read it, it's one of the conditions that you can use the sine law on. The other way, of course, that you can determine it is to know that you've got one given angle and its opposite side. Okay, so either way, you know that you can use the sine law on this. Okay, so take a look at the information that you're given. You are given angle A and side A. Okay, and how do we know that? Just if you aren't sure about this. The side which is opposite angle A is named lowercase a, and the side opposite angle B is named lowercase b, and the side opposite angle C would be named lowercase c. Okay, so I'm given angle A and side A, and I am given angle B, and I want to find side B. Okay, because I don't really know. I wasn't told I needed to find C. Okay, so you know our sine law is sine of A over side A and sine of B over side B and sine of C over side C. And because of the information that we're given, we will want to use the first two ratios. And so I'm going to look for sine of angle A, which is 108 degrees, over side A, which is 24. And that's equal to sine of angle B, which is 33 degrees, over side B, which I don't know. And then I cross multiply. And so I'm going to go B times sine of 108 is equal to 24 times sine of 33 degrees, and then because I want to isolate for side B, I'm going to divide both sides by sine of 108 so I can reduce on this side. And so I'm going to get B equals 24 sine of 33 degrees over sine of 108. Now I'm going to work that out on my calculator. And just a reminder that because we have two terms in our numerator, when I go to plug this into my calculator, I want to make sure that my numerator is in brackets. Okay, so I'm going to go bracket 24 times sine of 33 bracket, and then close the bracket off so that your whole numerator is within brackets, and then divide it by sine of 108, enter, and I'm going to round to the nearest whole number. Okay, and I will choose that because both angles in my triangle are whole numbers, and so is my side. Okay, so side B then is equal to about 14. Okay, so for our second example here, we don't have a diagram, so we are going to have to draw one. Okay, and we are told that triangle PQR has an angle P which is 36 degrees, a side P which is 24.8 meters, and a side Q which is 23.4 meters. And we've been asked to find the measure of angle R. So the first thing we need to do is draw our triangle. And so I'm going to draw a line here which I will call PQ. And angle P is about 36 degrees, so I'm going to draw something that I think is close to that. So something like this. Okay, 36. And I also see that side P, which is going to be over here, and side Q, which is going to be over here, that they are almost the same length. So I'm going to try and draw them as best I can to close to the same length. Okay, where P is equal to 24.8 meters and Q is equal to 23.4 meters. And my third angle is R, and its opposite side would be here. Okay, so I want to figure out what angle R is. And okay, right. I just had to look at this for a minute. Okay, so this is actually a two-part question. Okay, so we can use a sine law, and if you take a look, we have a side, and angle. Okay, so we have a side angle, which we know is the ambiguous case, which means I could or could not have a unique triangle. So there's always the possibility that I would have two answers on the triangle. For this particular one, you're only going to have one. We'll come back to it later and we'll explain why you only have one, but for now, just know that you have one answer. And the other thing that you know about this, and the reason why you can use a sine law, is because you have angle P and its opposite side, which is side P. So you know you can use the sine law on this one. Okay, so the reason why this is a two-part question is because I have angle P and side P, and I have side Q, and if I want to use the sine law, that means the first thing I need to do is find angle Q. Okay, so my first step is to find angle Q, and I can rewrite my sine law so that it reads sine of P over side P equals sine of Q over side Q. And so I will get sine of angle P, which is sine of 36, over side P, which is 24.8. And that's equal to sine Q, which I don't have. I don't have angle Q, but I do have side Q, so I can put 23.4 meters in the denominator. Okay, and we're going to cross multiply, so I'm going to go 24.8 times sine of Q equals 23.4 times sine of 36 degrees. Okay, and I want to isolate sine Q, so I'm going to divide by 24.8 on both sides. Okay, and the other thing is, because now I'm down to sine of Q equals 23.4 sine of 36 over 24.8, I know that if I want to find angle Q, I need to find the inverse sine of everything that's on the right of my equation. So I'll do that up here. So angle Q is equal to sine -1 of 23.4 sine of 36 over 24.8 Okay, so I'm going to put all of that into my calculator. Okay, now I'm going to be using lots of different sets of brackets here, okay, because I've got the big ones here, and I'm also going to have a set of brackets around the numerator because I need to group those before I divide. Okay, so I want to go second sine to get my inverse sine, and then so there's my first bracket for the outside brackets here. I want to set up an inside bracket for this one here, so I'm going to go bracket 23.4 times the sine of 36, and then close that bracket, and then divide it by 24.8 and close that bracket, and then enter, and I get 33.6834. Okay, so I know that angle Q is equal to 33.683. Now, I don't want to round off just yet because I haven't, well, actually I do. Sure I do. Okay, so I'm going to round this off to the nearest whole number because we are asked to find the measure of angle R to the nearest whole number, so I'll get Q to the nearest whole number. And that will give me 34 approximate. These are all approximate, right? Okay, so now my second step is that I can find angle R because I know all angles in the triangle add up to 180. So I'm going to go 180 degrees minus my 36 for angle P minus my 34 for angle Q, and that will give me 110 degrees. So angle R equals 110 degrees. And it's always good practice to label your diagram as you go along, so I should really have put 34 degrees in here right away. And then I can list that this is 110 degrees. Okay, so that's the end of examples 1 and 2. Alright, so example number 3, we're going to solve a triangle. And just a reminder that solving a triangle means to find all the missing sides and angles. So in triangle EFG, angle E is 43 degrees, angle F is 80 degrees, side G is 7.8 centimeters. Find the missing angle and sides. Okay, so let's start by naming our triangle E, F, and G, and side opposite angle E is E, side opposite angle F is F, and side opposite G angle G is G. Okay, what do we know? We know that angle E is 43 degrees, we know that angle F is 80 degrees, and what we know that side G is 7.8 centimeters. Okay, so what kind of a triangle do we have? We have an angle, a side, and an angle. And this is a situation where, yes, we have a unique triangle, but we don't have an angle with an opposite side, okay? But we can work it out, right? So let's start with angle G. So find angle G. You know that all your angles in a triangle add up to 180. So we're going to go 180 minus 80 minus 43, and we get that angle G is 57 degrees. So I'll put that on our diagram. And now see, we have an opposite side and an opposite angle. So we can either find side F or side E, doesn't really matter. Okay, so I'm going to find side F. Okay, and I'm going to use angle G and side G, so I'm going to go sine of G over side G is equal to sine of angle F over side F. And so I have the sine of 57 degrees over 7.8 is equal to the sine of 80 degrees over side F. And then I want F, so I'll cross multiply. So F times sine of 57 equals 7.8 times sine of 80. Divide both sides by sine of 57. And I get that F is equal to 7.8 sine of 80 over sine of 57. So F is equal to, and I put all of that into my calculator, and I get 9.2 centimeters. Okay, and I'm going to work it out to the nearest tenth because my side G is to the nearest tenth. Okay, so put that on my diagram. F is equal to 9.2 centimeters. Okay, and the last thing we're going to do is find our last missing item, which is side E. So we're going to find side E. And we have lots of information we can use now. I can use sine of G over G or sine of F over F. And I will go with G because that's the probably the most accurate information. It hasn't been rounded off. Okay, so I'm going to go sine of G over G equals sine of E over E. And so sine of 57 over 7.8 is equal to the sine of 43 degrees over E. Okay, and I'm going to take a little bit of a shortcut here. I'm going to solve for E right away. So to do that, I'm going to go 7.8 times sine of 43. And I'm going to divide by sine of 57. Okay, and so when I plug all of that into my calculator, I get approximately, and this is all approximate, right? 6.3, and I will put that on my diagram. Okay, so we have solved our answers, or our solution is that F is 9.2 centimeters, E is 6.3 centimeters, and angle G is 57 degrees. Okay, and that concludes example number 3. Okay, so for example number 4, we're going to do more than one step. We are asked to find the area of this triangle to the nearest centimeter squared. And so we will first determine what kind of a triangle it is and whether we can use the sine law or not. Okay, so we are given an angle and then a side and an angle. So this is an angle side angle, which means that we can use the sine law. The only thing is we don't have the angle opposite our side 10, but we can easily get that. Okay, and why don't we also, before we get going, label the vertices of our triangle. So let's say this is A, B, C. So this is side B, this is side A, and this is side C. Okay, so we want to do that just so that we can organize our thoughts. Okay, so the first thing that I want to do, if I want to use the sine law on this at all, I need to have the angle which is opposite my given side. So I need to find angle C. And so angle C is 180 minus 27 minus 45, which gives me 108 degrees. So this is 108 degrees. Okay, so now I have my side and its opposite angle. And I want to get the area of this triangle. Okay, which means because the formula for area of a triangle is base times height over 2, I need to know what the height of the triangle is, and the height of the triangle happens to be this dotted line right here. So there's a couple of ways I could do that. Okay, I could find side A, and if I know side A and I have this angle, then I can find H. Okay, because I got a right triangle here, so I can just use SOHCAHTOA to do that with, right? The other way I could do that is to find side B and then use this triangle to find side H by using SOHCAHTOA again. Okay, so I'm going to start by I'm going to find side A. Okay, so my second step then is to find side A. Alright, so I have the sine of angle A, which is 27 degrees, over side A, and that's equal to the sine of angle C, which is 108 degrees, over side C, which is 10. And I'm going to do my shortcut again. I'm going to go A is equal to 10 times the sine of 27 over sine of 108. And I get that side A, and I'm going to round it off to, well, I'm going to write it to several decimal places because I don't want to round off until the end. And so I get 4.7735. And so I will put that on my diagram, 4.7735. Okay, so now I'm going to find H. Okay, and I've got a right triangle here. Okay, so step 3 is find H. So I have to decide which trig ratio I'm going to use. I have angle 45, and the opposite side to 45 is H, and the hypotenuse is 4.7735. So the trig ratio that uses opposite and hypotenuse is sine, so I'm looking for the sine of 45 degrees, which is equal to the opposite, H, over the hypotenuse, which is 4.7735. And so H is equal to 4.7735 times the sine of 45 degrees, and I will get an approximate value for H, which is, and this is all approximate by the way because 4.7735 is rounded off, right? And I will get 3.3754. Okay, so H is 3.3754. Alright, so my last step then is to get the area, because I have all the information I need. I have the base of my triangle, which is 10 centimeters. I have the height of my triangle, which is 3.3754. And so area for a triangle is base times height over 2. My base is 10 centimeters. My height is 3.3754 centimeters, and so I will plug those numbers into my formula. And I get that my area is approximately 16.877, and I want to round it off to the nearest centimeters squared, so that would be 17. Okay, and I write myself a sentence. The area of the triangle is 17 centimeters squared. Okay, and that concludes this example. Okay, so we're going to take a look at the ambiguous case. And the ambiguous case means that we may not have a unique triangle. So when solving a triangle, you must analyze the given information to determine if a solution exists. if you were given the measures of two angles and one side, so angle, side, angle, then the triangle is uniquely defined. Now remember, angle, side, angle is the same thing as angle, angle, side. Both of these will give you a unique triangle. However, if you are given two sides and an angle opposite one of those sides, so you have side, side, angle, the ambiguous case may occur. And in the ambiguous case, there are three possible outcomes. You can have a situation where no triangle exists that has the given measures, therefore there is no solution. You can have a situation where there is one triangle that exists that has the given measures, so you have one solution. Or a situation where you have two distinct triangles that exist with the given measures, and therefore you have two distinct solutions. These possibilities are summarized in the diagrams below. Suppose that you are given the measures of side B and angle A of triangle ABC. You can then find the height of the triangle by using h equals b sine A. So let's see where they get that from. So let's draw a triangle, A, B, and C. And we know angle A, so I'm going to put a dot in that vertice there to show you we know that angle. And we are given side B, so I'll label side B. So let's draw an altitude in then for our triangle. So let's drop a perpendicular line from C to the base. And as you can, and let's call this point right here D. Okay. So you can see that we have a right triangle here, okay, which is called ACD. And let's label our height H. So if I'm given angle A, then the side opposite to angle A is side H. And for triangle ACD, the hypotenuse is B. So if I want to find or come up with an expression that uses angle A, H, and B, I'm looking at sine, right? Because H is opposite A and I have the hypotenuse. So the sine of A is equal to H over B. Now if you take a look over here, they're telling us that H equals B sine A. Well, I can get that by multiplying both sides of this equation by B, and so I get that H is equal to B sine of H, or A. So this expression will give me the height of my triangle. So in triangle ABC, angle A and side B are constant because they are given. Consider different possible lengths of side A. For an acute angle A, the four possible lengths of side A result in four different cases. Now, just a reminder that acute means between 0 degrees and 90 degrees. So your angle A will be between 0 and 90 degrees. Okay, so let's take a look at our four different cases. In our first situation, all right, so remember we are given angle A and side B. Those are constants, okay? So this is a given and side B is our given. What we want to know is what happens to our triangle when we're given certain lengths of A, okay, different possible A lengths. All right, well, let's take a look at the situation where A is less than H, meaning that A is shorter than the height of our triangle. In other words, A is less than the height of our triangle. All right, I just said that. Okay, so if I swing arm A, so let's say there's a hinge here, okay, and I swing arm A to the left. You can see that it's never ever going to touch the base of this triangle, okay? And because it's never going to connect with the base of my triangle, there is no solution, okay? So when A is shorter than the height, there is no solution. And remember, A has to be an acute angle. Okay, in our next situation, the side A has exactly the same length as our height, okay? So A is equal to H. Remember, B sine A is just another expression for the height, so A is equal to the height. And there's only one possible answer here, because even if I swung A out to here and it has the same height as h, it won't touch the base of the triangle on this side of the altitude of my triangle, the height of my triangle. And if I swing it to the left, it won't touch the base on the left either. Okay, so there's only one possible answer for this one here. Okay, let's say that A is greater than or equal to B. Okay, so it's either going to be the same length as B or bigger than B. So in our diagram, it's larger than B. And once again, think of it as being on a hinge, and I swing side A to the left. Okay, then there's only one possible answer for this. Okay, because A will meet up at point B on the base. If I swing it past point A on this side, it would probably meet over here somewhere, like right there. But then my angle A is no longer acute, and so I can't use this as a possible triangle because my angle A measurement has changed. And so there is only one possible solution for this diagram here. Now, if we take a look at this situation here, okay, where we have that the height is less than A. In other words, the height is shorter than A, but A is shorter than B. So the length of A is right in between the height and side B. Okay, then what I get are two possible answers, okay, because A can meet up with the base right here. Okay, so remember there's a hinge here. So I can bring A down to AB and it will meet here. And if I continue swinging it, so you see there's this red line here, if I continue swinging it along, it's also going to meet right here. Okay, and so I get two possible triangles. I get one that looks like this. Okay, so A, B, C, where this is A and this is B, and here's my given angle. Or I get this triangle, okay, where this is A, B, C, here's my given, this is side A and this is side B. So I get two triangles. I get one triangle where all my angles are acute, or I get a second triangle, and I get a second triangle where one of my angles is obtuse, and obtuse meaning between 90 degrees and 180 degrees. So with this one here, I get two possible solutions. Okay, so for an obtuse angle A, all right, and remember obtuse means between 90 and 180. There are three cases that can occur. All right, so here's my obtuse angle A. Here's my given B. I know what A is. And here's my side A. If A is shorter than B, then remember there's a hinge. If I swing it from left to right, it never ever touches the base of what could be the triangle. So no solution. If A equals B, so they're the same length, then if I swing A, okay, there's A. If I swing that from right to left, there's only one place where it's going to touch my base, which is right here, and I don't get a triangle. I just get two sides to what could have been a triangle. Okay, so no solution again. But if A is bigger than B, then when I swing it from my hinge at C, the only place that it will ever cross over A is right here at point B, and so I would get one solution. Okay, so that ends this discussion, and we will look into it a little more deeply in our next video. Okay, so in this video I want to go back to example 2 and show you why there is only one solution for a triangle that is side-side angle. And then I want to take a look at an example of an ambiguous case and just make some observations about the two triangles that we would get when the ambiguous case results in two solutions. Okay, so let's go back to example 2. We have a side-side angle triangle which we know could result in no solution, one solution, or 2 solutions. So why does this triangle give us 1? Well, what I would like to do is just to rename our angles, not P, Q, and R, but A, B, and C, which means that side P is actually side A now, and side Q is side B. And let's compare side A and B. We know that A is 24.8 and B is 23.4. And if you go back to your diagrams under the ambiguous case, you can see that when A is greater than or equal to B, you would have only one solution. And that's the case here. If you take a look, A is bigger than B, so longer than B. So A is greater than B, and therefore there is only one solution for this triangle. Okay, so I'm going to ask you to take out a separate sheet of paper, and I'm just going to add some notes in under here. Okay, and what I'd like to do is compare or just make some observations about a triangle that is an ambiguous case where you come up with 2 solutions. So we're going to take a look at triangle ABC. Okay, and we know that I'm going to give you that angle A is 45 degrees, side A is 15, and side B is 20. Okay, the first thing that I want you to be able to do is to look at this information and decide on whether you have an ambiguous case or not. Okay, so let's find the height. We know that the height for this triangle will be B sine A. And so the height is equal to 20 times the sine of 45 degrees. And you get that the height is 14.14. Okay, so you can see that the height is shorter than A and A is shorter than B. So what we have here is H is less than A, which is less than B. So 14.14 is less than 15, which is less than 20. And if you go to your chart up here, you can see that when H is less than A, which is less than B, you have 2 solutions. So we know that this triangle will have 2 solutions. Okay, now I'm not going to solve it for you right now. I've already done that. What I'm going to do is just show you what the 2 triangles are, and I just want you to make some observations about them. Okay, so here is the first triangle that you will get. Okay, where all the angles are acute. So you get A, B, C. You will find that we already know that side A is 15 and side B is 20, and that angle A is 45. That's what's given. When you solve this triangle, you will find that side C is 19.1, angle B is 70.5, and angle C is 64.5. Okay, the second triangle that you will get with this is the one where you have an acute angle. Okay, so here is A and our given angle of 45. Side B, which was given as 20, and side A, which was given at 15. And then when I went through and solved, I found that side C is 25.5 degrees, and angle B is 109.5 degrees, and side C is 9.1. Okay, so the first observation I would like you to make is that in the first triangle, so let's call this triangle 1, and let's call this triangle 2. The first observation I'd like you to make is that angle B in triangle 1 and angle B in triangle 2 are supplementary. Okay, so angle B in triangle 1 is supplementary with angle B in triangle 2. Okay, in other words, they add up to 180 degrees, right? That's what supplementary is. So 70.5 degrees plus 109.5 degrees equals 180 degrees. So when you're working on triangles that are ambiguous and you know you're going to have two solutions, you're going to find that your angle B in one triangle, your first triangle, and your angle B in your second triangle will be supplementary. Okay? Now, second observation is that your supplementary angles have the same sine ratio. Okay, so sine of 70.5 degrees and sine of 109.5 degrees should be the same. So let's check that out on our calculator. Okay, so sine of 70.5 is 0.9426, and sine of 109.5 is, look at that, 0.9426. Okay, so that's another observation that you can make with these two triangles. Okay, the other one that I would like you to make, this is our third one, okay, is that the sine ratio of sine 70.5 and sine 109.5 are both positive. Okay, so the sine ratios of sine 70.5 and sine 109.5. In other words, they are both equal to positive 0.9426, right? Both of them positive 0.9426. So what does that tell us? That tells us that these angles are in the first and the second quadrant, okay? And also that 70.5 degrees is the reference angle for 109.5 degrees. Okay. So we also know that 70.5 degrees is the reference angle for 109.5 degrees. Okay, so I'm hoping that these observations will help you when we work on the next question. Okay, so let's end this video here, and then I'll go on to the last example for this section in the next video. Okay, so we're going to take a look at our last example, which is not example 3, it's example 5. And we're going to use a sine law in an ambiguous case. Before we look at this example though, I just want to show you that I found this link here, which will take you to a Java applet that can help you visualize and explore the ambiguous case. It's an excellent applet, and it can also help you with some of your homework. So if you have time, have a look at it. Okay, so when you're working on these questions, the first thing that you really should do is determine whether it really is the ambiguous case or not. So I'm just going to do a little sketch over here of the triangle A, B, and C, where angle A is 30 degrees and B is 25 centimeters and A is 18 centimeters. And remember, we need to know what the height is if we're going to determine whether it will result in 0 solutions, 1 solution, or 2 solutions. So our height is h equals b sine of a. So h equals 25 times the sine of 30 degrees, and we find that it is 12.5. Okay, so that's equal to 12.5. Okay, so we want to make a comparison between h and A and B. Okay, so H is 12.5, B is 25, and A is 18. So you can see from the values that we have here that H is less than A, which is less than B, right? Because 12.5 is less than 18, which is less than 25. And if you go back to your chart on the previous page, you can see that when H is less than A, which is less than B, you will have 2 solutions. Okay, so that means we're going to get 2 different answers for this question. Okay, so we are told A is 30 degrees, side A is 18, side B is 25. We have to determine the measure of the other side and angles, and then round our answers to the nearest units. Okay, so we're going to have to divide our page in 2 because we are going to be working on 2 triangles simultaneously. Okay, so our first triangle is going to look something like this. So here is our side AB and our angle A, which is 30 degrees. Now B is a little bit longer than A, so we're going to draw it like this. So this is C. Okay, so this is 25 centimeters and this is 18 centimeters. And so what we're going to find is angle C and angle B and side C. And our other triangle, and so we'll try to get this 30-degree angle in here, A and B. So side B is 25 centimeters and it's longer than side A, so I think that's about right. This is C, this is 18 centimeters, and here is side C. Okay, so on both triangles we're going to look for angle C, angle B, and side C. So I'm going to start with angle B. Okay, and I'm going to use sine A over A, which is equal to sine B over B. And so sine of 30 degrees over 18 is equal to the sine of B over 25. And so using my little shortcut, sine of B is equal to 25 times the sine of 30 divided by 18. Okay, and so when I work this out, I see that the sine of B is about 0.6944. And so when I work out angle B, remember you need to use the inverse of the sine. and you get that angle B is approximately 43.98, which rounds off to 44 degrees. Okay, so we're going to find angle B on this triangle too. And if you remember from the previous video, the little discussion that we had on comparing the two triangles that we would get, you know that angle B from your first triangle is supplementary with angle B on your second triangle. And so to get angle B, you can just go 180 degrees minus 44, and you get 136 degrees. Okay? Now, the other way you can work this out is to remember that because your sine ratio is positive, and using cast, you know that sine is positive in the first quadrant as well as the second. So if you have an angle in the first quadrant that has a reference angle of 44 degrees, which is our first angle for angle B, right? And you were to draw that in the second quadrant, okay, then your reference angle would still be here at 44 degrees. So if I wanted to work out my second angle, which, why don't I just call it theta, I would go 180 degrees minus 44, which equals 136. And you can see that it matches what we have over on our second triangle. Okay? Alright, so angle B on the first triangle is 44 degrees, and angle B on the second triangle is 136 degrees. Okay, so the next thing that I want to find is angle C. All right, it's an easy one to do, and I really can't find side C anyway unless I have angle C, so I'm going to start with that. Okay, so our second step is to find angle C. Now that's an easy one because we already know two angles in our triangle, so we just have to minus those from 180. So 180 minus angle A, which is 30 degrees, minus angle B, which is 44 degrees, gives me 106 degrees for angle C on this triangle. So I will put that on my diagram. So this is 106 degrees. And on our second triangle, we'll use the same method. So we want to find angle C. I already know two angles in this triangle, so I'm going to minus them from 180. And I get 14 degrees. Okay, so this is 14 degrees. Okay, so now on both triangles I'm going to find side C. Alright, now I already have angle A and its opposite side and angle B and its opposite side, so I can use either sine A over A or sine B over B to get side C. So I will use the sine A over A on this triangle, and I'll use sine B over B on this triangle, and just show you that you'll get the same results. Okay. All right. So I'm going to find side C, and I'm going to use sine of A over A equals sine of C over C. And so I'm going to go for sine of 30 degrees over 18 equals sine of 106 degrees over C. So C is equal to 18 times sine of 106 degrees over sine of 30 degrees. And I get that side C is about 34.605, which rounds off to 35. Okay, so I'll put that on my diagram. Okay, and then I will work it out on the next triangle. Okay, and this time I'm going to use sine of b over b is equal to sine of c over c. Okay, so sine of b is sine of 136 degrees over 25, and that's equal to the sine of 14 degrees over c. And I get that c is equal to 25 times sine of 14 degrees over the sine of 136 degrees. And that works out to be about 9 to the nearest whole unit. And so I will put that on my diagram. This is equal to 9. Okay, so we've solved both triangles. And I'll just list the information here. So on our first triangle, we have that angle B is equal to 44 degrees. Angle C is equal to 106 degrees, and side C is equal to 35 centimeters. And on our second triangle, angle B equals 136 degrees, angle C equals 14 degrees, and C is equal to 9 centimeters. And that concludes example 3, and it concludes our lesson on the sine law.